Welcome to another exploration of the extraordinary. Tonight, we venture beyond our world into the infinite expanse above us, where reality proves stranger than any fiction we could write. What awaits us are truths that challenge everything we think we know about existence itself. This evening's journey will take us past blazing suns and frozen worlds, through clouds of cosmic dust, and into the hearts of collapsing giants. We'll discover places where the rules of reality bend, where time becomes fluid, and where the impossible becomes routine. You might drift away during our travels, or perhaps you'll stay with us until the very end. Either way is perfect. So settle in, let your mind expand, and prepare to see the universe in ways you never imagined. Our voyage begins now. Space contains more stars than grains of sand on Earth. When we try to count the stars, our minds struggle with the numbers. Current estimates suggest there are roughly 200 billion trillion stars scattered throughout the observable cosmos. To put this in perspective, if you gathered every grain of sand from every beach and desert on our entire planet, you'd still fall short of the number of stars burning in distant galaxies. Each one of those pinpricks of light represents a massive nuclear furnace, many far larger and more powerful than our own sun. Some shine for billions of years, steady and constant. Others flare to life and die in cosmic instants, explosions so bright they momentarily outshine everything around them. When you look up on a clear night, you're seeing only the tiniest fraction of what exists. The naked eye can detect perhaps a few thousand stars under ideal conditions. But that's nothing compared to what telescopes reveal. Every seemingly empty patch of darkness, when examined closely, turns out to be filled with galaxies, each containing billions more suns we'll never see directly. Light from distant galaxies is older than our planet. The photons entering our telescopes from the most remote galaxies began their journey long before Earth existed. Some have been traveling for over 13 billion years, setting out when the universe itself was still young. By the time this ancient light reaches our instruments, the galaxies that emitted it may have evolved beyond recognition or disappeared entirely. This temporal displacement means astronomy is inherently an act of archaeology. We don't study the cosmos as it is, but as it was. The farther out we look, the deeper into history we peer. The most distant objects visible to our most powerful telescopes show us a universe that was younger, smaller, and fundamentally different from the one we inhabit today. In practical terms, this means some of the galaxies whose light we're collecting tonight may no longer exist. The stars within them could have lived complete life cycles, born and died, while their final light is only now arriving at Earth. We're witnessing ghosts, echoes of cosmic events separated from us not just by distance, but by eons of time. A day on Mercury is twice as long as its year. Mercury's relationship with time is peculiar. This small cratered world completes one orbit around the Sun every 88 Earth days, but a single rotation on its axis takes 59 Earth days. The mathematics of this creates something remarkable. From the surface of Mercury, one day-night cycle, from noon to noon, actually lasts 176 Earth days, twice the length of its orbital year. If you could stand on Mercury's scorched surface, you'd witness the Sun moving backward across the sky at certain times in its orbit. The combination of Mercury's elliptical path and its rotation creates an optical effect where the Sun rises, stops, reverses direction for a time, then continues forward again before setting. It's a celestial dance, unique in our solar system. The temperature swings are equally extreme. Facing the Sun, the surface reaches 430 degrees Celsius, hot enough to melt lead. But without an atmosphere to retain heat, the night side plunges to minus 180 degrees Celsius. Few places in the solar system experience such dramatic contrasts. There are volcanoes that erupt ice instead of lava. On distant moons orbiting the outer planets, a different kind of volcanism occurs. Rather than molten rock, these cryovolcanoes spew water, ammonia, and methane from beneath frozen crusts. The lava is liquid or slushy ice, sometimes mixed with organic compounds, erupting at temperatures that would be considered freezing cold on Earth. Enceladus, one of Saturn's many moons, displays some of the most active cryovolcanism we've observed. Enormous plumes of water vapor and ice crystals shoot hundreds of kilometers into space from cracks in its surface, creating a steady stream of material that feeds one of Saturn's rings. Beneath that icy shell likely sits a global ocean, kept liquid by tidal forces from Saturn's gravity. Neptune's moon Triton also exhibits this phenomenon, with nitrogen geysers that erupt when seasonal warming causes subsurface nitrogen ice to vaporize. These eruptions are powerful enough to carry dark material high into Triton's thin atmosphere, where winds spread it across the surface in long, dark streaks. It's a reminder that volcanic activity isn't limited to hot, rocky worlds. Galaxies are cannibals that devour their neighbors. The universe operates on principles of growth through consumption. Larger galaxies frequently consume smaller ones in slow-motion collisions lasting hundreds of millions of years. Our own Milky Way has engaged in this behavior many times throughout its history, absorbing dwarf galaxies and star clusters that wandered too close. Evidence of past meals surrounds us. Stellar streams, long ribbons of stars orbiting our galaxy in unusual patterns, are the digested remains of smaller galaxies torn apart by the Milky Way's gravity. The Sagittarius dwarf elliptical galaxy is currently being shredded, its stars slowly incorporated into our galaxy's structure, as it makes repeated passes through our galactic disk. This cannibalism isn't violent in the way we typically imagine. When galaxies merge, stars rarely collide because the distances between them are so vast. Instead, the gravitational interactions reshape both galaxies, sometimes triggering massive waves of new star formation as gas clouds compress and collapse. What emerges is something new, a hybrid born from two separate histories. Time travel to the future is physically possible. According to Einstein's theories confirmed by countless experiments, traveling forward in time is not only possible but inevitable when approaching the speed of light. An astronaut traveling at 99% of light speed would experience time passing normally, but upon returning to Earth, they'd find decades or even centuries had passed. This isn't theoretical speculation. We've measured this effect with atomic clocks on aircraft and satellites. GPS satellites must account for time dilation, adjusting their clocks because time moves slightly faster in orbit than on Earth's surface. Without these corrections, your navigation would be off by kilometers. Particle accelerators provide even more dramatic proof. Unstable particles that would normally decay in microseconds survive much longer when accelerated to near-light speeds. From the particle's perspective, time passes normally. But from our frame of reference, its clock has slowed, allowing it to exist longer than it should. The future is accessible through velocity and gravity. The past, however, remains beyond our reach. Every theory that allows backward time travel also introduces paradoxes that seem insurmountable. The universe appears to have a directional arrow, and we can only move along it in one direction. Some planets orbit dead stars. When massive stars explode, you might think any planets in the system would be destroyed. But sometimes they survive, and occasionally new planets form from the debris. Pulsars, the rapidly spinning remains of exploded stars, can have planetary systems orbiting them in the aftermath of stellar death. The first exoplanets ever confirmed were found around a pulsar designated PSR B127+12 in 1992. 3 planets orbit this cosmic lighthouse, bathed in radiation that would sterilize any surface. These worlds likely formed from the debris of the supernova itself, or are the rocky cores of gas giants whose outer layers were stripped away by the explosion. Life as we know it couldn't exist in such an environment. The pulsar's intense radiation and magnetic fields would be instantly lethal. Yet the planets persist, following their orbits with mathematical precision in conditions that would annihilate anything we recognize as alive. They're monuments to persistence, worlds that refuse to be destroyed even when their sun died violently. The coldest temperature in the universe was achieved on Earth. While space can be incredibly cold, the coldest temperature ever recorded occurred in a laboratory here on our planet. Scientists have cooled atoms to within a billionth of a degree above absolute zero, colder than anywhere else in the known universe, including the depths of interstellar space. Absolute zero, minus 273.15 degrees Celsius, represents the point where atomic motion theoretically stops entirely. Getting close to this temperature reveals quantum mechanical effects that are invisible at normal temperatures. Atoms begin behaving as waves rather than particles, and matter enters strange states with properties unlike anything in our everyday experience. The cosmic microwave background, the residual heat from the Big Bang, provides a temperature floor for natural space at about 2.7 degrees above absolute zero. Anything in the universe will eventually warm to at least this temperature through exposure to this ancient radiation. To go colder requires active intervention, shielding from this background glow, and sophisticated cooling technology. Saturn's rings are vanishing before our eyes. The magnificent rings that make Saturn instantly recognizable are temporary features, and they're disappearing faster than we previously thought. Every second, approximately 10,000 kilograms of ring material falls into Saturn's atmosphere, pulled down by gravity and dragged inward by magnetic fields. This ring rain consists mostly of water ice, with some rocky material and organic compounds mixed in. As it enters Saturn's upper atmosphere, it vaporizes, creating subtle changes in the planet's chemistry that we can detect spectroscopically. At the current rate of loss, Saturn's rings could largely disappear within 100 million years, perhaps sooner. The rings themselves are surprisingly young, possibly only 10 to 100 million years old, which is recent in astronomical terms. They may have formed when a moon or large comet ventured too close to Saturn and was torn apart by tidal forces. For a brief moment in cosmic history, Saturn wears this crown of ice. Future civilizations billions of years from now may look up at a ringless gas giant. There's a giant storm on Jupiter that's been raging for centuries. The Great Red Spot, a storm system larger than Earth itself, has been churning in Jupiter's atmosphere since at least 1831, when continuous records began. Historical observations suggest it may have existed even longer, possibly appearing in sketches made in the 1660s, which would give it an age of over 350 years. This anticyclone rotates counterclockwise in Jupiter's southern hemisphere, with winds reaching speeds of 430 kilometers per hour at its edges. Unlike hurricanes on Earth, which lose energy when they make landfall, Jupiter's storm has no surface to disrupt it. It feeds on the planet's internal heat and the energy of smaller storms it absorbs. Recent observations show the Great Red Spot has been shrinking. Measurements from the late 1800s indicated it was about 41,000 kilometers across, but today it spans only about 16,000 kilometers. No one knows if this contraction will continue until the storm disappears entirely, or if it will stabilize at a smaller size. Jupiter keeps its secrets close. You could survive in space for 90 seconds. Without a suit, Hollywood often depicts explosive decompression when someone is exposed to the vacuum of space, but reality is different. While certainly fatal after a short time, vacuum exposure doesn't cause your blood to boil or your body to explode. Your skin is strong enough to hold you together. The immediate danger is lack of oxygen. You'd lose consciousness in about 15 seconds as oxygen-depleted blood reaches your brain. Before that, you'd experience embolism, where water in your tissues forms vapor bubbles, causing severe swelling. Your lungs would be damaged if you held your breath, as the air inside would expand rapidly. But if you exhaled and didn't panic, you could remain conscious for those critical seconds, and if brought back into a pressurized environment within about 90 seconds, you'd likely survive with medical treatment. Several people have experienced brief exposure to near-vacuum conditions in accidents, and some have survived with minimal lasting effects. The largest structure in the universe is a supercluster, the Hercules Corona Borealis. Great Wall is a structure so vast, it challenges our understanding of how the universe can organize itself. This galactic filament stretches approximately 10 billion light-years across, making it the largest known structure in the cosmos. It contains billions of galaxies arranged in a pattern like a cosmic web. Structures this large shouldn't exist according to some cosmological models. The universe hasn't been around long enough for gravity to pull together something of this scale, yet there it is, detected through the distribution of gamma-ray bursts across the sky. Its existence suggests our models of how large-scale structure forms may need refinement. Flying through this region at the speed of light, you'd spend 10 billion years in transit, crossing from one end to the other. For context, the universe itself is only about 13.8 billion years old. This single structure spans a significant fraction of the entire age of existence. Jacure. Neutron stars can spin 700 times per second. The fastest spinning neutron star yet discovered rotates 716 times every second. This pulsar, designated PSR J17482446 AD, is turning so rapidly that its equator moves at roughly 25% the speed of light. Any faster, and centrifugal force would tear it apart, despite gravity that can flatten atoms. These stellar remnants are incredibly dense. A neutron star packs 1.4 times the sun's mass into a sphere just 20 kilometers across. A sugar cube-sized piece of neutron star material would weigh about 100 million tons on Earth. This density is mind-bending, approaching the limits of how compressed matter can become before collapsing into a black hole. The rapid rotation is a consequence of conservation of angular momentum. When a massive star collapses, it's often rotating slowly. But as it shrinks to a tiny fraction of its original size, it spins faster, like a figure skater pulling in their arms. The result is a cosmic whirligig, a stellar corpse spinning at rates that push the boundaries of physics. Mars has blue sunsets. While Earth's sunsets paint the sky in reds and oranges, Mars offers the opposite view. As the sun descends below the Martian horizon, the sky around it glows blue, fading to butterscotch and pink overhead. This reversal happens because Mars's thin atmosphere is filled with fine dust particles that scatter light differently than Earth's atmosphere. On Earth, our thicker atmosphere scatters blue light in all directions, making the sky blue during the day. At sunset, light travels through more atmosphere, scattering away all but red wavelengths. On Mars, the fine dust particles are just the right size to scatter red light during the day, but allow blue light to penetrate during sunrise and sunset. Photographs from Mars rovers show this alien beauty clearly. Watching the sun set on another world reminds us that the rules of light and atmosphere produce endlessly varied results. Each planet offers its own palette, painted by the unique combination of gases, particles, and light interacting in ways specific to that world. There's a planet made of diamond. Approximately 40 light-years away orbits a world unlike any in our solar system. Designated 55 Cancri E, this exoplanet is thought to be largely composed of carbon in the form of diamond and graphite. With temperatures reaching 2,400 degrees Celsius, it's a jewel world, though not one you'd want to visit. The planet's unusual composition stems from its formation. Born in a carbon-rich environment with little oxygen or water, the available materials crystallize differently than in our own solar system. Mathematical models of its interior suggest that a significant portion of its mass may be crystalline carbon, essentially making it a giant, hellishly hot diamond. Its surface might feature seas of liquid carbon and mountains of diamond, all under a sky glowing from the heat of its nearby star. The planet orbits so close to its sun that a year lasts just 18 hours. In such conditions, any surface features would be constantly reshaped by extreme temperature gradients and tidal forces. The Milky Way's black hole is surprisingly quiet. At the center of our galaxy sits Sagittarius A, a supermassive black hole containing about 4 million times the Sun's mass. For something so massive, it's remarkably inactive. Most of the time, it barely feeds, emitting only weak radiation as small amounts of gas trickle across its event horizon. Other galaxies harbor black holes that blaze like beacons, gorging on massive quantities of material and blasting out jets of energy that span thousands of light years. Sagittarius A appears to be resting, perhaps because the central region of our galaxy has been swept relatively clean of easily accessible material. Occasionally, it flares up. Observations have captured brief episodes where its brightness increases dramatically, possibly when an asteroid or small gas cloud falls in. But these are minor snacks compared to the feeding frenzies at other galactic centers. Our central black hole is like a sleeping giant, powerful but peaceful, for now. Some asteroids have their own atmospheres. We typically think of atmospheres as features of planets and large moons, but even small asteroids can hold on to thin envelopes of gas. Ceres, the largest object in the asteroid belt, releases water vapor from its surface, creating a tenuous atmosphere. The vapor likely comes from ice sublimating when certain areas are exposed to sunlight. These asteroid atmospheres are incredibly thin, millions of times less dense than Earth's, barely qualifying as atmospheres at all. Yet their existence tells us something important about how water and other volatiles are distributed throughout the solar system. Many asteroids that appear dry and barren may actually contain significant ice deposits beneath dust-covered surfaces. The European Space Agency's Rosetta mission studied Comet 67P and found it surrounded by a cloud of water vapor, dust, and organic molecules, a primitive atmosphere created by solar heating. As we study more small bodies up close, we're learning that the boundary between active objects with atmospheres and dead ones is less clear than we once thought. Your body replaces atoms that were once in stars. Every breath you take contains atoms that have cycled through countless other forms. The oxygen entering your lungs may have once been part of a distant star, forged in nuclear reactions, then scattered across space when that star exploded. Over billions of years, these atoms found their way to Earth, into the air, and now into you. Similarly, the carbon in your cells, the calcium in your bones, and the iron in your blood all originated in stellar furnaces. Heavier elements require extreme conditions to form, found only in the cores of massive stars or in the violent moments when stars explode. Every atom heavier than helium in your body was created in such events. This is more than metaphor. The atoms making up your body at this moment are constantly being exchanged with your environment. You breathe out carbon dioxide that plants incorporate into their structures. You eat food whose atoms become part of you. You are not a static object, but a dynamic pattern, a temporary arrangement of stardust that thinks and feels before dispersing again. The universe has a speed limit for information. Einstein's special relativity established that nothing can travel faster than light, but this limit extends beyond just physical objects. Information itself cannot propagate faster than light. This means the universe has a fundamental speed limit for cause and effect, creating a cosmic postal system with built-in delays. When you observe a distant supernova, you're seeing an event that occurred years or centuries ago. The explosion happened, and the information about it spread outward at light speed. No technology, no matter how advanced, could have received that information sooner. This isn't an engineering challenge to be overcome, but a fundamental feature of space-time itself. This limit has profound implications. It means there's no universal now that extends across the cosmos. Events that appear simultaneous from one perspective occur at different times from another. The universe operates on a network where messages can only travel at one speed, creating a structured web of causality. Planets can wander between star systems. Not all rogue planets drift alone forever. Occasionally, a stellar wanderer can be captured by a new star system, becoming a permanent resident. The complex gravitational interactions during such captures could explain some of the unusual orbital patterns observed in exoplanet systems, where planets circle their stars at odd angles or in extremely elliptical paths. These adoptions are rare events requiring precise conditions. The incoming planet must arrive with just the right velocity and angle to be caught by the star's gravity, without crashing into other planets or being flung back into space. When capture succeeds, the result is a world with two histories: its original formation in one system and its new life in another. Some astronomers suspect that Triton, Neptune's largest moon, may actually be a captured Kuiper Belt object, rather than a moon that formed alongside Neptune. Its retrograde orbit, moving opposite to Neptune's rotation, suggests a violent capture event in the distant past. Space smells like burnt steak and hot metal astronauts. Returning from spacewalks consistently report a distinctive smell clinging to their suits and equipment. The odor is described as metallic, like welding fumes, or similar to seared meat. This smell isn't space itself, but rather the byproducts of what happens when equipment is exposed to the space environment. One theory suggests the smell comes from high-energy particles and radiation interacting with materials in the vacuum, breaking molecular bonds and creating reactive compounds. When these materials return to the air-filled spacecraft, they oxidize rapidly, releasing volatile molecules that our noses interpret as that distinctive burnt metallic scent. Another possibility involves polycyclic aromatic hydrocarbons, complex carbon compounds found throughout space. These molecules may adhere to spacesuits and equipment during spacewalks, then off-gas once inside. Whatever the exact mechanism, the scent is apparently universal, and memorable enough that astronauts across decades have mentioned it. The solar system has a tail. As our sun travels through the galaxy, it creates a bubble called the heliosphere, carved out of interstellar space by the solar wind. This bubble isn't spherical but teardrop-shaped, with a long tail stretching behind the sun as it moves. This heliotail extends for billions of kilometers, possibly reaching distances comparable to Pluto's orbit. The shape is created by the interaction between the solar wind, a constant stream of charged particles from the sun, and the interstellar medium, the thin gas that fills the space between stars. As the sun plows forward at about 70,000 kilometers per hour, the heliosphere stretches behind it like a comet's tail. Only recently have we begun mapping this tail's structure using data from distant spacecraft. The Voyager probes, having left the main heliosphere, are sending back information about this boundary region. It's yet another reminder that even our solar system is a moving, dynamic structure, not a fixed island in space. Some binary stars are so close. They share an atmosphere. In the most extreme binary systems, two stars orbit so closely that their outer layers touch, creating a common envelope of gas surrounding both. These contact binaries exchange material constantly, with gas flowing from one star to the other, and sometimes forming bridges of plasma between them. Such systems are unstable over long timescales. Eventually, the stars may merge completely, forming a single, rapidly rotating star. Or one might strip material from its companion so aggressively that only a core remains, creating unusual stellar remnants that don't fit normal categories. W Ursae Majoris systems are the most studied examples of contact binaries. In these systems, both stars orbit inside a shared envelope of gas, creating a peanut-shaped configuration. Their surfaces can't be distinguished as separate anymore, yet two distinct cores orbit within this shared atmosphere. A cosmic embrace so close it defies our usual sense of objects being separate. Gravity waves are ripples in space-time itself. When massive objects like black holes orbit each other at relativistic speeds, they create waves that propagate through the fabric of space-time itself. These gravitational waves compress and stretch space as they pass, though the effect is incredibly tiny. The first direct detection in 2015 measured a distortion smaller than a proton's width. These waves travel at the speed of light, carrying information about the events that created them. When two black holes merged 1.3 billion years ago, the collision released more energy in a fraction of a second than all the stars in the observable universe combined. That energy radiated outward as gravitational waves, finally reaching Earth in 2015. We now have multiple detectors listening for these cosmic ripples, opening a new way to observe the universe. Gravitational wave astronomy doesn't rely on light, so it can reveal events that would be completely invisible to traditional telescopes. We're hearing the universe's deepest bass notes, vibrations in the structure of reality itself. The emptiest place in the universe is emptier than we can imagine. Most of space is already remarkably empty, with interstellar space containing perhaps 1 atom per cubic centimeter. But cosmic voids, vast regions between galaxy filaments, are emptier still. The Bootes void, discovered in 1981, spans approximately 330 million light-years and contains remarkably few galaxies. Within this void, the average density drops to perhaps 1 galaxy per volume that would contain hundreds elsewhere. These voids aren't truly empty, but they come as close as nature allows in our universe. They may contain dark matter, but regular matter, the stuff that makes stars and planets, is almost entirely absent. These voids formed as gravity pulled matter into filaments and clusters, leaving increasingly empty regions behind. As the universe expands, the voids grow larger, and the contrast between dense regions and empty ones becomes more pronounced. In the far future, these voids will dominate the structure of the cosmos. We're accelerating away from distant galaxies. The universe's expansion isn't slowing down as gravity pulls everything together. Instead, it's accelerating. Distant galaxies are receding from us faster now than they were in the past, driven by a mysterious force called dark energy that makes up roughly 68% of the universe's total energy content. This discovery, made in 1998, was completely unexpected. Astronomers were trying to measure how much the universe's expansion was slowing, assuming gravity would eventually halt and reverse it. Instead, they found expansion speeding up, a result so surprising it was checked and rechecked before being accepted. Dark energy behaves unlike any form of matter or energy we understand. It appears to be a property of space itself, exerting a gentle but persistent repulsive force. As the universe expands, more space comes into existence, which means more dark energy, creating a feedback loop that will eventually drive distant galaxies beyond our ability to ever observe them. There may be hidden oceans. Throughout the solar system, liquid water might be far more common than we once thought. Europa, Enceladus, Titan, Ganymede, and possibly several other moons likely harbor subsurface oceans beneath their icy crusts. These hidden seas may contain more water collectively than all of Earth's oceans combined. These oceans persist in the cold outer solar system because tidal heating keeps them liquid. As these moons orbit their planets, they're stretched and squeezed by changing gravitational forces, generating internal friction that produces heat. This process can maintain liquid water even billions of kilometers from the sun. Where there's liquid water and energy, there's potential for life. Scientists are planning missions to sample the water plumes jetting from Enceladus, or to drill through Europa's ice to search for organisms. The possibility that we're surrounded by potentially habitable oceans on distant moons has reshaped our search for life beyond Earth. The largest known star would reach beyond Jupiter's orbit. UY Scuti, among the largest stars we've found, has a radius approximately 1,700 times greater than the Sun's. If placed at the center of our solar system, this red supergiant's outer layers would extend past the orbit of Jupiter, engulfing everything inward, including Earth. Despite its immense size, UY Scuti contains only about 30 times the Sun's mass. Its outer atmosphere is so diffuse that it's more like a hot fog than what we typically think of as solid or even gaseous. You could fly a spacecraft through these outer regions, experiencing temperatures of thousands of degrees but almost no resistance. Stars this large burn out quickly, living just a few million years before, exploding as supernovae. Their short lives mean they're relatively rare, and we've found only a few dozen candidates for largest star. Measuring them accurately is challenging, because their boundaries are poorly defined, their atmospheres gradually fading into surrounding space. Cosmic inflation expanded the universe faster than light. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. Space itself expanded faster than light could travel through it, growing from subatomic scales to potentially many times larger than the currently observable universe in less than a trillionth of a second. This rapid inflation explains several puzzling features of our universe. It explains why space appears flat on large scales, and why the cosmic microwave background has nearly uniform temperature, despite regions being too far apart to have ever been in contact. Inflation stretched tiny quantum fluctuations to cosmic scales, providing the seeds for all future structure. The physics of inflation is still being refined, but the evidence supporting it continues to grow. It suggests our observable universe is just a tiny patch of something vastly larger, perhaps infinite. Inflation may even be ongoing in other regions beyond our view, continuously creating new universes in a process called eternal inflation. And there we are. We've traveled far tonight, across distances that would take light itself billions of years to cross. We've seen worlds of fire and ice, storms that dwarf our planet, and objects so dense they challenge our understanding of matter itself. Every fact we've encountered is real, verified by observation and mathematics, yet each seems almost too strange to believe. The universe is not just larger than we imagine, but larger than we can imagine. It operates on scales both vast and minute that our minds struggle to grasp. Yet here we are, collections of atoms organized in ways that allow us to contemplate it all, to reach out with telescopes and equations, and begin understanding this incredible place we call home. As you drift off, remember that you're made of the same materials as the stars we've discussed. The iron in your blood was forged in a supernova. The calcium in your bones was created in stellar cores. You are, quite literally, the universe observing itself, a temporary pattern of stardust that has become conscious. Tomorrow the cosmos will still be there, waiting with more wonders to discover. For now, rest easy knowing that reality is far more magnificent than any dream. Good night, and may your thoughts drift among the stars.